Hello, everyone. Welcome to the Reinforcement Learning Reading Club. In this session, we will be reading this paper from New Rips 2021, if I'm not wrong. And the presenter will be Riad Akrour, the postdoctoral researcher in the Aalto Robot Learning Lab. So we can begin.
All right. So I didn't prepare slides for this presentation. I'm just gonna open up the paper, and of course, feel free to interrupt me, and that it's like a discussion rather than a presentation. Because the papers is very rich and cover like two very different things put together, and I think it has a few interesting things. But of course, like if you want me to focus on something in particular, or if something is not clear, don't hesitate to interrupt me. So the main two things of the paper is this unsupervised part. So where they don't have a reward, a task-specific goal to achieve, but they want to explore the environment and try to learn like a diverse set of skills. And then there's this second part about the domain adaptation. And specifically, they want to adapt when there is a change in the dynamics. So some of the examples they have in the experiment is sim to real. So like you have a source environment where you train, or you do most of the training in simulation, and then you want to transfer to a real robot, and you will collect throughout the training some trajectories on the real robot, but it will be much less than what you would do in the simulator. And so yeah. So okay, let's and so although it's so for not trying to solve a specific goal, and it has this domain adaptation part, it will all boil down to just a reinforcement learning task. And so the goal is to phrase these two kind of objectives, to have the unsupervised part or to have the domain adaptation as rewards. And then once you phrase these objectives as rewards in a reinforcement learning setting, so basically a function of the state and action space, then you can apply a reinforcement learning algorithm. So here specifically they apply SAC, but so yeah, the general idea is to try to phrase these two things as a reinforcement learning problem, and then use an off-the-shelf RL algorithm to solve this. And so maybe quickly before going into this, so this is also something we discussed, for instance, in the last meeting with Amin and so on, about other approaches to sim to real. So it's not the main focus of this paper, but it's one of the applications of this dynamics aware rewards. So the main difference here is, and so the ideas that are presented in these papers, they can be also combined to other ideas of sim to real. So it's not like it's orthogonal to things like domain randomization that we discussed last time and so on, where you try to learn a policy on many different environments in simulation, with the hope that it includes, in some sense, the real environment that you will then have on the real robot. And here they want to do something a bit more refined, in that they will also kind of have some samples from the real environment, and then penalize states where the dynamics are very different between the simulator and the real world. So they will try to adapt the policy such that it avoids maybe unstable states, or states where there is a large difference between the simulator and the real world. And these ideas like can be combined, like they're not like they can be combined. domain adaptation, domain randomizations, and the idea of this paper. And so, okay, so let's start. So as I said, now the main goal is, so okay, maybe here first there are some of the examples. So I talked about sim2real, but you can also have some other applications where in the target environment you have some obstacles in additions. And so if you train policies in the source environment, if you don't take into account these obstacles, you will end up with skills that do not reach the goal. So here you have some kind of trajectories, and like the big blob at the end is the goal of this goal condition policy that you want to reach. And so you can see that with their method, just sampling a few trajectories from the target, but then training on the source, you can try to avoid this region of the state space where you have large differences between the dynamics of the source and the target. And so you learn skills that work well also in the target environment. And so, as I said, like we are not trying to solve a specific, or they are not trying to solve a specific task, but they have some kind of intrinsically motivated algorithm. So the main objective is this one. So forgetting the differences in environment and so on. So the main objective is just to maximize the mutual information between goals and targets and trajectories that you generate with your policy in the target environments. This is the main goal. And so the mutual information, so basically it's high if you generate, so you have a distributions over goals that has a lot of entropy. So you don't focus on just one goal, but you have a distribution that is wide and covers, for instance, the state space if your goals are to reach specific states. But the other term of mutual information is that you are able to, so once you see a given trajectory, you are able to recognize which goal it is. And so the point of this is that that the trajectories are actually reaching the goal, because like you can generate a goal distribution that can be like very wide and have a lot of entropy. But of course, if the trajectory is then if the policy, for instance, don't take into account the goal condition and then always generate the same thing, then of course we wouldn't have learned anything useful. And so you need, for a specific goal, you need to generate like a different trajectories that goes to this goal. And so this is the point of the second term, that if you observe a trajectory, you are able to, then the entropy is very small on the distribution of goal, because for a given trajectory, you can recognize what the policy is trying to do and which goal it's trying to go to. Whereas if you didn't learn anything and the policy actually doesn't depend on the goal, then it will like do the same things or very similar things irrespective of the goal. And so you will still have high entropy here, which is not good. So these are the two terms. You want to generate diverse set of goals, and then you want to actually learn policies that can reach these goals, and then will naturally generate trajectories that are dissimilar given the goal. So this is, yeah, please.
Yeah, so is the goal space similar to the state space, or is it like the same vector as the state, or how do you
so in some of the trajectories, yes, the goal is a state in the state space, but and sometimes it's something more abstract. It's just some vector in some arbitrary space in some like latent space. But in the case where the goal is in the state space, of course, like so one of the challenge here is how to sample in this state space. Like, how do you sample meaningful goals? And so this is where it starts. So the next progression is to then introduce this latent space to represent the goals, and this you will also learn how to sample meaningful goals in the state space by sampling first in this latent space. So this is so which part is this, where so you will have two policies. So you will first sample a goal in the latent space, and then you will have this policy pi u here. So this one, you will maximize the mutual entropy between these goals in the latent space and the trajectories generated by pi u. And then so for instance, if you want the goals to be in the state space, then you would relabel. So you pick, so it's stated, I think, around here, the relabeling. So yes, sub goals can be like this latent representation itself, or you can just pick the final state of the trajectory. So by minimizing this, by learning PyU using goals in the latent space, then you can pick whatever end state of this trajectory tau tilde, and then this would be a goal in the state space if you want to have like goals that are maybe a bit more interpretable and so on. And then you can, and so the distribution of omega of goals in the latent space will also induce a distribution in state space through sampling from the policy PyU. So that's how you learn kind of a distribution over the state space also. But in some of the experiments, they don't bother with this, and they just have goals in some latent space. It still generates diverse scales, and in that case, maybe the use of having these two different policies is not very high. But yeah, if you want to generate goals in the state space that are maybe a bit more interpretable, then this is what they propose to have. Two types of policies. One that will optimize the abstract goal, and then you get the goal in the state space by picking the last state of the trajectory. All right. Does this answer the question?
Yeah, but I'm now wondering why they needed this omega. Why not directly sample the goal? Like from the actual...
So because it's not always easy to sample from the state space. So imagine, I don't know, you are doing something from vision, right? And how, like, I don't know, you want your character, if it's an Atari game, for instance, or something like that, like you want your character to reach a given position, or like grab the key or something, and it's not easy to sample an image that does this, right? So because
yeah, thanks.
But yeah, maybe some tasks like, I don't know, maybe Mujoko or something where you have angles and you know the range of the angles and so on. Maybe it's a bit easier, right? And so then the second step is so this part was about learning diverse skills, but then there is also the part about having like a difference between source and target in the environment. And so going from this first objective of just maximizing the mutual information, they introduce some kind of penalty that will measure the KL divergence between trajectories generated from the same policy, but on the source and the target environment. So you want to learn a policy that generates. So now the objective now is not in the target environment, but in the source environment. So you learn in the source environment a policy that has high mutual information between the goals you generate and the trajectories that are generated by the policy, but at the same time that do not go into that. So if you apply the policy in the target environment, the trajectories would be very similar, whether it's in the source or in the target. And of course, it looks like it would be hard or expensive, and that you don't gain much from this, because you will always need to compute this in source and target, but you will so they will learn some kind of discriminator here that apparently generalize quite well, and you can only learn this from a few samples, whereas the reinforcement learning part, like this part, to learn this policy will take more samples, and so it's beneficial to have this part in the source and the penalty learned efficiently with a few samples from the target and the source. So the next step is what we talked about, because goals, you cannot easily sometimes sample states in the state space. So they introduce latent variables from this, and that's why you have now two policies in the source environment, one to kind of generate trajectories for the abstract goals, and then you relabel from trajectories tau tilde to get the goal in the state space and so on, but the rest is the same. Learning steps is mostly how to phrase this as a reinforcement learning problem, where you have functions that only depend on the current state and not on trajectories. So there are a few inequalities that they use. So the first one, so there is this inequality. I didn't know it before reading the paper, but apparently it's very fundamental inequality in information theory. That if you have so a graphical model like this, or a Markov chain, where you have conditional independence of one variable knowing, so for instance here tau is conditionally independent of omega knowing the goal. So if you know the goal, then, and because this policy will depend directly on the goal. So if you know the goal, then the distribution of tau will be independent from the distribution of omega. And so if you have this kind of Markov chains, then you have these inequalities that so additional transformations cannot increase information, and so the mutual information between this and this is higher than the mutual information between this and this. And this is the inequality they use to kind of bring back the mutual information of omega here instead of the goal. So I think one of the main advantages is that it reduces a little bit the number of discriminators that we'll need to learn, which we'll talk about. But okay, so this is mostly technical and will help with the training. And the second one that you can get also from the same data processing inequality will help to phrase. So now if you pick any of this mutual information term, so they use this inequality to go from an objective that is with respect to a full trajectory to an objective that is with respect to a full state. And it's the same kind of inequality, because so you have some omega. The omega will generate some trajectory, and from the trajectory you can pick any of the states. And so if you know the trajectory, then the state is conditionally independent from omega. And so then the mutual information for a specific state will be lower. The mutual information for a specific state and omega will be lower than the mutual information for the full trajectory and omega. And you can do this for all the states in the trajectory, and then you can take the average. And this is what this inequality is about. And this helps to phrase now things in terms of state and not trajectories. And then, so this is just a rewriting of what does the conditional entropy is. And so you get this term. So it's the entropy of the goal distribution. And so the distribution are sampled. The omegas are sampled from a fixed prior. So you have some goals. I don't know, for instance, I think in some of the experiments they have like a finite number of goals. So this, like there is so they use, for instance, like a uniform distributions over different goals, and then it's just a one-hot encoding for the omegas. That it's, I don't know, goal 1, goal 2, goal 3, and so on. And of course, it doesn't, like there is no real, like it's not in the state space. But then through the these two objectives combined, you will be able to relate a goal in this abstract space to a goal in the state space. But so this entropy is fixed. It's not something you optimize, because they have a fixed prior over omegas that they do not optimize. And then so this part, so it's the expectations over. So what is this? The abstract goals to generate and the induced state distribution of this log probability. So the probability of being in a specific goal given a given particular state. And so to be able to compute this, they use a learned kind of density function that they optimize by maximum likelihood. So you have a trajectories of states, and for each state, you know which goal the current policy is following, right? So you have a data set, and then they learn this distribution by fitting this parametric model. Because from the positivity of the KL, we know that this term will be smaller than this term, because this term minus this term is the KL between this distribution and this distribution, and this is always positive. But yeah, so now it's something that you can actually implement and easily compute and also solve by reinforcement learning, because so you learn this density function, and then this density function will give you a reward each time you visit a set of how, basically it's how well you can like classify or recognize the goal you are following, given simply from observing a particular state. And this goes back to what we were saying before, that we want to like be able to recognize the goal if we see a particular trajectory, because it means that the policy is actually depends on goals, and and is doing different things for the different abstract goals that we are setting. And this is so for one of the mutual information term. And you can do exactly the same to bring back, so the same inequalities to go from this mutual information term to something that also depends on the state. And so in their implementation, they use the same kind of density, the same discriminator for both. So the only difference is that one is on trajectories generated by pi mu, and the other one is by trajectories generated by pi theta. But it's the same process. So learning this density function, and then this gives you like a function that depends on the state, and so you can optimize it by reinforcement learning. And so they then have phrased like a reward version of these objectives and this objective. And the last thing is to have something that you can phrase as like a reward function for this last part. And so for this last part, which is the KL divergence between trajectories executed in the source and the target environment from the same policy. So it will have a very simple form actually, because so this is the probability of the joint probability of a given goal and a given trajectory in a given environment. And you can see that, so it has this decomposable shape. And so you sample a goal, you sample an initial state, and then you follow the policy at every time step, and the transition follows the given dynamics. And because it's the KL between the same policy, it's just the environment that changes. So it's the same distribution of goals, the same policy, the same initial distribution, and so on. And it's just this thing that will change. So when you will compute the KL, like the part of the KL that is the log of the ratio between trajectories generated in the source and in the target, all these things will cancel out, and you will only have this part that remains. So at the end, this KL will only be the expectation over trajectories generated in the source, which we have samples of this delta R, which is the log ratio between the transition in the source and in the target. And so basically the interpretation is that you will penalize being in or observing transitions that have a large difference in likelihood between source and target. So you want to only stay in regions of the state and action space where you will observe kind of same dynamics. But if you go in regions of the state action space where the dynamics are very different between source and target, then you will have a higher penalty. So this delta R will be high.
Excuse me, so
yeah.
Does it mean that we require to have the transition functions of the source and the target environments?
So they will also then learn these things from samples. So you only need a few samples from the target and from the source. And they will, so this is the last step now.
Okay.
And so yeah, how to compute this when you don't have the model of the source and the target. And so you will learn two discriminators. So similarly to before, So one discriminator we take as input state, action, and next state, and we'll predict whether it comes from the source or the target. And the other discriminator will only take source and action, and will do the same thing of predicting whether it comes from the source and the target. And if you simply apply Bayes rule, so basically here, here it's the probability to be in ST plus 1 given ST, AT, and being in the source environment. So like this is the meaning of this. And here is the same, like the probability of going to ST plus 1 given ST, AT, and being in the target environment. But what they learn is kind of reversed. So not predicting the next state, but predicting whether you are in the source or the target from ST80, ST plus 1, and ST80. And then, so starting from this, so like just applying Bayes rule that, I don't know, probability of being in ST plus 1 given ST80 and source is, I don't know, probability of being in ST plus 1 given ST80. So so like the prior and then the likelihood, so probability of being in the source given ST80, ST plus 1 divided by probability of the source given only ST and AT. And so there will be one extra term, which is just the transition, irrespective of whether it's the source of or the target. But these things will cancel out. So yeah, if you just apply Bayes rule here, you will see that you can rewrite these equations using these two discriminators in the following way. So you only need like these two discriminators that predict whether you are sourcing or target given ST80, ST plus 1, or only ST80. And you can compute this reward.
Yeah, okay.
But so yeah, I mean, so you don't have a model, you kind of not learn it, but at least learn to discriminate where it comes from, either from model 1, the source, or model 2, the target. And so but it is equivalent to basically try to avoid to avoid state actions or in general to avoid transitions when you can easily predict if it's coming from the source or the target. So you don't want to, yeah, so you want to stay in so it's the same idea of, and so it's here it's not like an, oh, of course there is an approximation because here you are like learning model and not using the true model. So this is not actually, so maybe the notation here is a bit wrong. It's not exactly delta R, it's just an approximation, but so apart from approximation from like the learning, the fact that we are learning the model and not, or learning this discriminator and not using the true probabilities, but the rest is the same, and it's a similar intuition. You want to avoid a transition where you can easily distinguish if it comes from the source or the target. And yeah, so this is the overall algorithm at the end. So maybe we can go through it, some kind of recap, basically that. So the general setting is that you have a source environment and you have a target environment. And so this is a hyperparameters. It tells you how many, so what's the ratio between source and target. So how many samples you get from the source and how many from the target. So I think in the experiment, they get 1 trajectory from the target for every 10 trajectory from the source or something like that. And so so the goal is to learn this policy theta. that is able to do like different kind of skills, and that these skills would work both in the source and the target. The different parameters that you have is the parameter of this policy, so theta, but also the parameters of the policy that optimize the abstract goal and not the goals defined in the state space. Because so you need different parameters, because so like if I don't know if this is a neural network or something, like the input of this neural network would be a goal, would be like some kind of state, and a goal state in addition of the current state, of course, like other policies in reinforcement learning. But the input of the other policy would be like this abstract goals, which can be like just a one-hot encoding or some vector, maybe in some continuous space or something like that. And then you have the parameters of all the discriminators I mentioned. So for approximating this delta R, where is it? So the one that kind of penalize going into states that are different between source and target, and then the discriminator for saying if you are able to distinguish the goal from the trajectories or actually just from a single state. So yeah, and so then yeah, you start by, so you have a fixed prior of your goals. You start by sampling this abstract goal, and you can then like plug this goal to the current policy PyU, and it will generate trajectory data that you will add to this set of rollouts. And then using the set of rollouts, you can train this discriminator that will try to predict omega from the states only that are in this data set. So in this data set, you will have trajectories and omegas, and you try to predict omegas from states. And then so this Q5 will give you the reward, as we said. So this would approximate like the part of the mutual information that predicts if you have recognizable trajectories given, or that the trajectories can help you predict the goal. And so this is a reward in the state space. So you can easily then use any algorithm. Here they use SAC to update the policy. So this is updating PyMu. And then, so for the other policy that now depend on goals that are potentially in the state space, so they don't always do this step of relabeling in their experiments, but in some experiments they do it. And so here you have to train kind of another policy, but it's a very similar process that, so you pick, so you call this relabel, which for instance would pick the last state of this trajectory. And then you do the same thing that you would create also trajectory data in the source environment again. And also trying to learn the discriminator. So, okay, no, this is the wrong one, but I don't know if they mentioned also that they would train this discriminator also from the trajectories that are generated by this, but I guess they should do it. I don't know if it's mentioned here, I don't see it, but yeah. So what they say is that you would also, so here, depending on your hyperparameters of how frequently you would get data from the target environment, you would also do a few rollouts on the target environment. And these rollouts will then help train the other classifier that predicts whether a given transition comes from target or source environment, which, yeah, will update this the parameters of this discriminator, and then this gives you like the full reward for training by theta which will then depend on like the part about learning distinguishable trajectories for specific goals, and then the part about trying to avoid transitions where you have large discrepancies between target and source, and again you can use SAC. So yeah, this is, I guess, an overview of the algorithm. And the experiment, so I mentioned these maps and this sim to real, and they also have some other experiments where so it's the source environment is, I think, the standard Mujoko environment, but then the target is some environment where you cripple some of the joints. Yeah. Yeah, so they do it for half cheetah and the ants, and then so the target environment you cripple some of the joint, and I think they do the same also for the humanoids, and for the quadruped it's simtorial. And yeah, so we already had a glimpse of the results, but thanks to this term that tries to avoid like being, for instance, in the state space here, you would learn skills that, yeah, like do not go through this wall. And they also do another experiment with shorter and longer obstacle. And so I don't know exactly what the plot about the ant is showing. Careful details, but maybe you avoid using so maybe you avoid using like joints that do not work on the target or something like that. I'm not sure I can interpret this easily, but yeah. And they also have like this so this is the rewards that you learn from the discriminator about the trajectories. Yeah, it's just to show that it will not give you goals, I guess, that would be in the obstacle. And here it's plots of the rewards. So if you have trajectories that go in the obstacle, or maybe in a state where in the target environment you will have an obstacle, then you have like this large penalty that will penalize. So this comes from the KL term. Yeah, and so on. So I guess it covers pretty much everything. So they mainly compare to their prior work, which was about learning different skills, but didn't have this notion of domain adaptation between source and target. And then they also compared to dark, which is actually a very similar work, but it's not. So this is another paper that's from iClear 2021. So it's also relatively recent. So it's very similar in that it proposes this idea of it has very, very similar ideas for adapting from source and target dynamics. And I guess, up to also using this discriminator and so on. And so basically you can see this paper as combining the skill, learning diverse skills from this prior work of the same authors, and then learning or adapting to domains from this other paper. Yeah. So yeah. I guess it covers like these two papers. And unfortunately, I didn't find the video. Maybe I didn't search well enough. but I didn't find a video for the real robot thing experiment. So here the goals, I think they only had 2 goals, and which ended up being working forward and backward, and they don't have really, so it's I don't know how clear it is, like what they compute, but yeah, it just shows that you need less samples if you follow this than if you fine-tune directly. If you learn something in simulation and you fine-tune on the real robots, you will need a bit more trajectories, maybe because you don't avoid these states, and so you need to adapt a bit more, or if you train directly on the robot. But yeah, there is not more details on this. So yeah, that basically concludes the paper. So I don't know if there are other questions.
Yeah, thank you very much. Yeah, I would also be interested in seeing the video results for the humanoid character. Yeah, but
maybe there are. Oh, actually there are. Okay. So I don't know if.
Oh, okay.
Because this is like first iteration. Or maybe this is the trajectories. Oh no, this is okay, fine tuning. So fine tuning, I guess it's you learn in simulation and then you do RL on the real robot, starting from the policy learning simulation. So I don't know. Yeah, I don't know if that was like the last policy, or I guess it would also be interesting to see like the trajectories they collect while learning, like to be able to train this discriminator that tries to figure out whether a transition comes from the real world or something like that, or from the simulation. But this seems to be directly the last policy, I guess. It looks maybe a bit too good.
Yeah, I guess so.
Yeah.
So are there any questions or comments from the audience?
And I wonder how it is related to diversity is all you need paper.
I know diversity is all you need paper in evolutionary computation. Is this what you are talking about, or there is also an RL version of it?
No. That's the paper where they learned skills in also in unsupervised RL setting, but they learned the skills also by maximizing mutual information between the goal, the final state, and the state that actually happened. So they learn to control the final state distribution, and then just no. They first sample a skill, and then they maximize mutual information between that skill and the final state. So this way they just learn.
So I guess one of the main difference would be that like this step of not knowing how to sample from the goal, but having to sample from this abstract latent representation, and then picking the goal from the trajectories of pi mu to get then a goal. Because so not in this paper. So here they set it So I think in their thing, they just say that they don't do like all these works, they do not do transfer from different environments and so on. But I guess it's not the most maybe interesting comparison, because I mean, yeah, so your question is, if we forget about the change in dynamics, what's the difference between this and diversity is all you need? And so I don't know diversity is all you need, but maybe one of the difference is that in diversity is all you need, you have to sample the goal from the state space, which is maybe a bit hard. Like in the previous paper, I don't know if I can find this, from the same authors, they had also experiments in Atari, and yeah, I guess in that setting, maybe it's a bit hard to sample like goals in Atari, like to sample goal images. And so I think the main contribution of that, of this PIM paper is that you have this two policies, like one that depends on abstract goals and then one that depends on perceptual goals in the state space.
Yeah, but like paper after paper on the topic of unsupervised RL, they become more and more difficult to read, actually. Does anybody have the same feeling? They're very complicated.
Sorry, what?
Like every paper on unsupervised RL become more and more difficult to read. So it's very, very difficult algorithm with a lot of losses and so on.
I see. Yeah, so to be honest, I don't know the literature that well, but I think one of what makes this paper like complicated is that it's combining two ideas that don't really need to be studied at the same time, right? Like learning a supervised RL is one thing, and then domain adaptation is another thing, and you have losses for both that are maybe a bit complicated. And so when you do both at the same time, it's also becomes longer, but I guess they don't really need to be studied at the same time. And so this is the prior work from the same author, and it focuses only on this pi-mu and pi-theta to generate different goals, and it doesn't have the change in dynamics. They have maybe a bit richer experiments in terms of setting goals, because they have things in Atari, which maybe is a bit harder. And yeah, this could be one of the difference with the paper you cited.
Yeah, okay, thanks. I will take a look at it. Very interesting presentation.
Yeah, okay, so is there any other questions or comments? Okay, so thank you, Riad, for the presentation. And thank you everyone for joining, and see you next week.
Bye-bye.
Bye-bye.
Thanks.